Okay, to review Kepler's laws, Kepler's first law is that all orbits are elliptical. Orbits are elliptical. And that means that if something is orbiting, like if we've got the Earth and a satellite, and that satellite is orbiting, it's going to orbit in some elliptical orbit with the Earth at one focus. Remember that for an ellipse has two foci. So the Earth is going to be at one, and there's going to be another focus. And we talk about the major axis and the minor axis, etc., of the ellipse. But the satellite is going to go around one of the foci of the ellipse. That's Kepler's first law. Kepler's second law is equal areas and equal time. We spent enough time on that. Equal areas and equal time. And we justified it qualitatively. But equal areas and equal time can also be written as the time rate of change of area, dA dt, equals a constant. That means that it's that a planet orbiting a sun or a star sweeps out the same amount in area per unit time, no matter where it is on the ellipse. And then Kepler's third law is that the period of rotation is proportional to the radius cubed for any orbit. So that means that the smaller the radius of orbit, the smaller the period. In other words, the faster it's going to go because the smaller the amount of time it takes to get around. So I just want to go ahead and justify a little bit further Kepler's second and third laws before we move on to the energy of orbits, or the energy related to the gravitational force. We are going back and forth here between gravitational force and orbits. If something is under the gravitational force, it will either is influenced by the gravitational force. It'll either be attracted to a massive object, or it will orbit around that massive object. So one of the results of the gravitational force is orbits. So let's just look at Kepler's third law. Kepler's third law is easily shown from Newton's second law, right? If the gravitational force is G m1 m2 over r squared on some object, let's draw the objects m1, m2, and they're separated by some distance r. If the force on m1 due to m2 is gm1 m2 over r squared, or the force on m2 due to m1 is gm1 m2 over r squared, they will each feel that force equally. In any case, if we're talking about, let's fix m1 and just look at m2. So we'll pin this in place. Let's go ahead and pin this in place, right? So pin it down. That's a pin. And look at the motion of m2. So we can say that the net force, F net, equals ma. If this is orbiting, right, m1 is pinned down, m2 is orbiting m1, then the net force is going to be the gravitational force, g m1 m2 over r squared, equals m2 v squared over r, right? That we're looking at the net force on m2, and the acceleration of m2 is v squared over r. Well, since v is equal to 2 pi r over t, at least assuming it's a circular orbit, we can at least do this argument easily for a circular orbit. If it's 2 pi r over t, then we can write that g m1 m2 over r squared is equal to m2 times 2 pi r over t squared divided by r. So just plugging in 2 pi r over t for v. We then go ahead and solve that equation, and we end up getting that you can see on the right-hand side, we're going to get a t squared. On the left-hand side, we're going to get a I take that back. On the left-hand side, if we cross-multiply, put t on the left and r on the right, on the left-hand side, we're going to get a t squared. On the right-hand side, we're going to get an r cubed, and then we're going to have a bunch of constants. So it's going to be something like t squared g m1 over 2 pi squared is equal to r cubed. So we get t squared gm1 over 2 pi quantity squared equals r cubed. So therefore, you see that for a circular orbit, at least we've proven that the period squared is proportional to the radius cubed. So this is just a result of Newton's second law. F net equals ma. Newton's law of gravitation, gmm over r squared equals ma, mv squared over r. It's just a result of that formula that we've been using numerous times. Sometimes proportionalities can help save a little time, right? So if we don't worry about the constants, we can write, so therefore t, I'm just going to write t is proportional to r to the 3/2. T squared is proportional to r cubed, is the same as taking the square root of both sides. T is proportional to r to the 3/2. Then we can say, let's ask a question like we talked about how the period of rotation at or near the Earth's surface is about 90 minutes, right? So for example, t is approximately 90 minutes at a radius of Earth's radius away from the Earth, if we're orbiting the Earth, right? So if we have the Earth and we have some little tiny satellite or big fat satellite like the Earth station, the space station orbiting the Earth, it's about 90 minutes when it's close to the Earth's radius. I know that the picture I drew, it's beyond the Earth's radius, but we're close to the Earth's radius, it's 90 minutes. Let's say that we want to double that. Let's say that we want to find the radius at which t is equal to 3 hours. So we want a t new equals 2 t original, and we want to know what the r new is. R new equals what, right? How many Earth radii away? So we said, well, t, which was 90 minutes, would be proportional to something times the Earth radius to the 3/2. So t new must be 2 times t, so it must be 2 times re to the 3/2.